So in this lecture, we would like to present vectors. As we're going to see, we're going to be interested in two-dimensional and three-dimensional vectors, basically. Operations between vectors and the properties of those operations. We're going to see that the vectors give us a prototype for what is going to be called a vector space, even though in this course, we're not going to use vector space, abstract vector spaces. And then we're going to look at the coordinatization of vectors. It will be pretty straightforward once we have coordinates to talk about the magnitude of vectors, even though that is a notion which is independent of coordinatization. And finally, we're going to talk about unit vectors. So let's get started by what a fixed vector is. So a fixed vector, so this is one step before defining the vector the way we're going to use it. A fixed vector is an oriented line segment. So we're talking about a line segment that starts at a given point, ends at another point. We can use an arrow in order to denote the head of the vector. And let's say if it starts at A and ends at B, we could denote it by AB with a little arrow on the top. So in general, though, in this course, we're going to talk about free vectors. In other words, we're going to identify two fixed vectors if they share three characteristics. First, they're parallel. So if you extend the vectors to get lines, those lines are parallel, they never meet. There is one case in which you cannot really do that. That's if you have a vector that starts and ends at the same point. And in that case, we will identify all those vectors that start and end at the same point. We're going to call them, as we're going to see, the zero vector. But we will want them to, they point the same direction. This is not such a rigorous mathematical statement, but I guess for two-dimensional and three-dimensional vectors, it should make perfect sense. So for example, if I have these two vectors, they point to the same direction. If I have these two vectors, they point in opposite directions. And let's agree that we're going to say that two vectors point the same direction, if and only if, I'm sorry, we are going to talk about this notion only if we're dealing with parallel vectors. So if you have two vectors that are not parallel, we're not going to even bother about saying whether they point to the same direction or not. And finally, they have the same length. And this way, we form free vectors, or the vectors that we're going to be talking about in this course. So in other words, strictly speaking, a vector is going to be not just an oriented line segment, but in fact an infinity of oriented line segments that have that share these three characteristics. And one of the main properties of this definition is that given, so if U is a vector, we're going to denote them with, for example, small letters with an arrow, or you can find them as bold-faced small letters without any arrow in the book. So if U is a vector and A is a point, then there exists a unique point B so that the vector U is AB, is the same as the vector AB. What do I mean by this? So suppose that I have a vector U right here. Okay, I'm not specifically interested in where it begins and where it ends. Remember, I have infinitely many choices for where a vector will begin, but I'm given a point A. So basically what I'm saying is that you can find a unique point P so that the vector AB is going to be the same as the vector U. In other words, you can make a vector originate anywhere you like, okay, as long as you preserve the three properties, the three characteristics that it has: the line to which it's parallel, the direction that it points to, and the length. And as we said, these three characteristics apply to vectors with non-zero length. On the other hand, all vectors that have zero length form the same, belong to the same vector. They are the same vector, which we're going to call zero vector. So let's make this note here. So the zero vector is defined by vectors that, I mean, fixed vectors, but I'm going to drop the term fixed vector. I'm just going to talk about vectors from now on that originate and terminate at the same point. And the zero vector is going to be denoted by a zero with an arrow on the top. Now, let's see what operations we can have between vectors. So first of all, we have addition of vectors. How does this work? Let's say that you give me a vector U and a vector V. And even though you see that I have not used it so far or said it explicitly, we're working either in a two-dimensional space or a three-dimensional space. So imagine that we're given two such vectors. Then remember that I can take any point and make U originate at that point. And now the trick is that where U terminates, I'm going to make V originate. And then I'm going to connect the point of origin of U with the terminal point of V. And that's how I am getting U plus V. Please note that if you were to use two other representatives, meaning vectors that share the same characteristics with U and V respectively, you would have got a vector that also shares the same characteristic with the vector that I found right now. And this gives us the sum of the two vectors. Then we have a scalar multiple of a vector, or scaling a vector by a real number. So the idea here is rather simple, and we could describe it with a few examples. So let's say that you start with a vector U. In order to consider 2U, you just take a vector which is parallel to U, points the same direction, and has twice the length of U. And then if you want to consider negative 3U, you take a vector that has 3 times the length of u, but points the opposite, oops, I said points the opposite direction, but points the opposite direction than the vector from the vector u. And here's your negative 3u. Okay, and if you want 0u, then it's going to be the 0 vector. So 0 times u is going to be just the 0 vector. Now, you can pretty much fill out the rest of the definition in the case that you don't have the number 2 or you don't have the number negative 3. It's going to work the same way with any positive number and any negative number. And for 0, we just said what this is. The interesting thing is that by scaling a non-zero vector, you can get any other vector which is parallel to that vector. And that's a very, very important remark that is going to be very, very useful. So two non-zero vectors u and v are parallel if and only if there exists a number, a real number, in our case, lambda. This is a standard Greek letter which is used in this context. It's pronounced lambda. Such that u is equal to lambda v, or v is equal to lambda u. You can take it either way, obviously not with the same number. It will be the reciprocal that you will have to use if you want to express the other vector in terms of the second vector in terms of the first. And please note here that in this definition, we could actually allow one vector to be the 0 vector. The 0 vector is thought of as being parallel to any vector. Okay, so in other words, we could just say that by all vectors parallel to the non-zero vector vector u are given by lambda u, where lambda varies over all real numbers. At this point, we would like to discuss the properties of these two definitions that we gave, the properties of the operations between the two vectors. And you're going to see that we're going to present the properties in a very formulaic way. We're going to give 8 properties that in a different context are used as the axioms for the definition of a vector space. But in our case, we will just say what's going on with these two operations. And here are the properties. So the first property, imagine that you have 3 vectors, u, v, and w, and you want to add them up. The way that we presented addition, you can add just 2 of them, right? So at the time. So you would have 2 ways of doing this. So you could take u and add v to it. And once you find the sum, then you can add w. Or you could begin with v then add W, and once you have found the sum, then add U. Basically, the first property says that if you do it either way, you're going to get the same result, and this is known as associativity. The second property says that if you add the zero vector to any vector, you get pretty much the vector that you have in front of you. So, in other words, there exists a vector z such that u plus z is equal to z plus u for equals to the vector u for any vector u. This property would be dubbed existence of an additive neutral. Existence of neutral element for addition. And at this point, we should note that this vector z, the vector z with this property is unique. And is none other than the zero vector. Yeah, it's exactly the zero vector that has this property. The third property says that given a vector u, there is a vector v such that u plus v is v plus u is equal to the zero vector. This property could be dubbed as existence of additive inverse. And again, it's a little exercise in math formalities to show that the vector v alluded to in this property is unique and will be denoted by negative u. In concrete terms, if we look at the vectors that we have studied so far, what you do is you take a vector which is parallel and has the same length, but points the opposite way. So you reverse pretty much the direction of u. That is how you find negative u. And that allows you pretty much to define subtraction. So subtraction between two vectors is by definition adding the first vector with the opposite of the second vector. Okay. The fourth property is rather simple, is that if you add two vectors, then the order in which you add them does not matter. This is known as commutativity. As you can see here, for all of these properties, I could have written for any u and v, for any u and v and w for the first property. I'm just trying to keep the notation as simple as possible. Then we have two properties that have to do with the interaction between addition and scalar multiplication. So basically they say that if you have two vectors, you add them up, and then you want to scale their sum, it's the same thing that you will get if you scale the first vector, then scale the second vector, and then add them up. Okay? And then there's another property that works the other way, meaning if you have the sum of two numbers and you want to scale a vector by the sum of these two numbers, then you can scale the vector first by the first number, then by the second number, and you can add them up. Here, let me note, a small thing that this letter is read μ. Okay. The next property looks very, very obvious. I mean, why would anybody state anything like that? But again, as I said, I'm stating these properties because these are the standard defining properties for a vector space. And pretty much here, the seventh property is that if you scale a vector by the number 1, then you just get the same vector. Finally, the last property says that if you want to scale a vector by the product of two numbers, then what you could do is scale it by one of the numbers, and then when you have scaled it, you can scale the result by the other number, and you're going to get the same thing. And here, please notice that because of the commutativity of multiplication for real numbers, that also means that this would have been the same thing as first scaling by lambda and then scaling by mu. So these properties establish the fact that the set of two-dimensional or three-dimensional vectors that we're going to be working with forms a vector space. So according to these properties, the sets of two-dimensional and three-dimensional vectors are vector spaces. But as I said, this is a notion that would be of interest to somebody taking linear algebra or knowing about linear algebra. However, it is a good idea to just note this property at this point. In order to be able to do more things with vectors, we have to define coordinates. We have to coordinatize the whole approach to vectors. And we're going to see how this is done in 2 and 3 dimensions. So imagine, let's say that we are in 2 dimensions first. And if we are in 2 dimensions, then we can define, or we can have a Cartesian system of coordinates. We can assume the existence of a Cartesian system of coordinates. And if we have a vector u somewhere here, then what we do is we take u to originate at 0, 0. And we just read the coordinates of its terminal point. So let's say that those coordinates are A and B. Okay, this is how we denote the coordinates in this coordinate system, with A and B in a parenthesis. Then we define the coordinates of the vector u. as exactly these numbers, A and B. And in order to distinguish between coordinates of vectors and coordinates of points, we use this diamond bracket. So this is for vector. And when you see something like this will be a point. And of course, this can be done in 3 coordinates. So in 3 coordinates, let's be careful about how we would sketch our 3 coordinates like this. Okay, so we have, this is the x-axis, this is the y-axis, and this is the z-axis. So think about it this way, the y and the z-axis are the axis of the paper we're looking at, and x comes out of the paper like this. And again, imagine that you have a vector u, and you pretty much do exactly the same thing. So you force u to originate at 0, 0, 0. Its terminal point is on point A, B, C, and you take the coordinates of the terminal point to be exactly the coordinates of u. Okay, so the vector u now becomes the vector ABC. And this way, every vector acquires coordinates, whether you are in 2 dimensions or 3 dimensions. Of course, it might be a concern now if somebody gives us a vector somewhere, most probably they will give us the point where it originates, the point where it terminates. How do we find the coordinates? Is there some easy way? And the answer is there's a very, very easy way. So, and here's how it works. If you have a vector u that originates at A1, B1, and terminates at A2, B2, so this is the vector u, then it turns out that in order to find its coordinates, you just subtract the coordinates of the point of origin from the coordinates of the terminal point. So you have A2 minus A1, comma B2 minus B1. And same thing in 3 dimensions. So you have a vector u, and then you have the point of origin of that vector, A1, B1, C1, and its terminal point, A2, B2, C2. How do you find the coordinates of u? You will subtract the coordinates of the point of origin from those of the terminal point. So A2 minus A1, B2 minus B1, and C2 minus C1. And of course, as usual, it would be meaningful here to do some examples. So imagine that you have the vector AB, which starts at the point A1, 3, and ends at the point B, 2, 7. Can you give the coordinates of AB? And also, let's do this for 3 dimensions. So here I have the vector AB that starts at the point 1, negative 1, 2, and terminates at the point 3, 1, negative 1. So can you find the coordinates of these 2 vectors in each of the 2 cases? Please pause the recording, find the coordinates, and then check your answers with what I'm going to do. So I'm going to give you a couple of seconds. And we're going to have 2 minus 1 for the first coordinate, that gives you 1. And for the second coordinate, we will have 7 minus 3, which is 4. So the first vector is going to be 1, 4. And the second vector, we're going to have 3 minus 1, which is 2 for the first coordinate. 1 minus negative 1, that's again 2 in the second coordinate. And negative 1 minus 2, which is negative 3 for the third coordinate. So again, let me just say here how I found those numbers. So this number 1 was 2 minus 1. The number 4 was 7 minus 3. The number 2 here was 3 minus 1. The number 2 was 1 minus negative 1. And finally, the number negative 3 was negative 1 minus 2. Okay, and that's how we found the coordinates of these vectors. Now, we actually have that these coordinates work perfectly when you combine them with the operations. So it turns out that if you have two vectors, let's say you have the vector u is equal to u1, u2. So its coordinates are u1 and u2. Sometimes we also call them components. And the vector v had components v1 and v2, or coordinates v1 and v2. Then it turns out that the vector u plus v has coordinates which are exactly sums of the corresponding coordinates. So u1 plus v1 would be the first one, and u2 plus v2 would be the second one. And if you want to scale, let's say you can scale either one, but let me scale u, then its coordinates are going to be lambda u1, comma lambda u2. Okay, again, it's a good idea to do a couple of examples so that this sticks with us. So let's say that you have u is equal to 1, 5, and v is equal to 2, negative 3. I would like you to compute the coordinates of the vectors u plus v and negative 3u, and 2v. Okay, please compute the coordinates of these two vectors. Again, pause the recording, do this little exercise. I'll give you a couple of seconds. And here are the answers. So you will find 3, 2. How did I find 3, 2? I add 1 plus 2, that's 3, and 5 plus negative 3, that's 2. And then here I get minus 3, negative 15. And here I get 4, negative 6. Okay. Occasionally, there are going to be numerical errors here, and I apologize in advance. Since I don't have a live audience, they might not be caught. But in any case, this allows us to actually work with vectors in a very, very specific way. So if you start with a vector AB, then by using these properties, you can say, first of all, right away that this is the vector A, 0 plus the vector 0, B. We could actually see geometrically what this means, but this is besides the point at this juncture here. And this is A times the vector 1, 0 plus B times the vector 0, 1. And pretty much what I'm going to say is that we have a very special notation for these two vectors. So from now on, this is going to be the vector I. We're not going to use I for anything else in this context. And this is going to be the vector J. Okay. And so basically, we end up being able to write our vector as AI plus BJ. Sometimes we say that these two vectors, the vectors I and J, represent the standard basis for vectors in 2 dimensions. Guess what? Working exactly the same way, we can do this for 3 dimensions. So we can write A times the vector 1, 0, 0. So I'm speeding things up a little here. B times the vector 0, 1, 0. Plus C times the vector 0, 0, 1. And again, we will have special names for these vectors. There should be no confusion here, because hopefully the dimension of the space we're working with is going to be clear from the context. So this will be the vector I, this will be the vector J, and this will be the vector K. And we will avoid to use these letters for any other vectors in this context. So in some sense, we will reserve them for this purpose. And so this will be AI plus BJ plus CK. And again, it's a good idea to do an example. So why don't we start with the vector 5, -3, and write it in terms of the basis vectors, and do the same with the vector 1, 3, -7. Okay, again, I'll give you a couple of seconds to pause, and then you can check the answer. And the answer is, of course, this is 5i minus 3j. I could have written plus -3j. It's pretty much the same thing. And here 1i, I can just write this as I plus 3j minus 7k. Yeah. Nice and simple remark. We will use these vectors on a very regular basis. And here I would like to make another very, very interesting remark regarding parallel vectors. Because now that we have coordinates, it's very easy to find whether two vectors are parallel or not. So let's say, for the sake of the argument, that somebody asked us to determine whether the following two vectors are parallel. So determine whether the vectors 1, 3, -5, and 2, 6, 7 are parallel or not. Okay, again, I invite you to pause the video, try to do it yourselves based on what we have seen. And then in 2 seconds, I'm going to explain how this is done. So how can we decide whether these two vectors are parallel or not? We said that two vectors are parallel, if especially two non-zero vectors. So these two vectors are non-zero. They're parallel if and only if one is a scalar multiple of the other. So let's say that I want to write the second vector, 2, 6, 7, as some number times the first vector, 1, 3, -5. So how can I do this? I mean, the first thing I'm going to look at is the first two coordinates. Okay, so can I scale? How can I scale 1? With what should I multiply 1 in order to get 2? And the answer is this number has to be 2, right? I mean, there are not too many options for this one. It has to be 2. Yes, but unfortunately, so 2 doesn't work for all the coordinates. So you see, just by looking at the two coordinates, this the number is determined. It has to be 2, but it doesn't work for the other coordinates. So this works for the first coordinates. It also works for the second coordinates, but not for the third. And there are no other candidates. I mean, you have to have something that works for the first coordinate. It's the number 2 that works for the first coordinates and nothing else, but it doesn't work for the other coordinates. So guess what? The answer is that they're not parallel. So the vectors are not parallel. I should say here that another instance of vectors that are easily seen not to be parallel are when you have two vectors, and let's say one has a 0 where the other does not. So if you look at these two vectors that I just wrote, just by spotting the fact that on the third coordinate, this has a 0 and the other vector that does not, we can conclude that they're not parallel. Why? Because there is no way to scale the second vector, or I should say the first vector, so as to get the second vector, right? Anything you try to scale the first vector by, it will give you 0 on the third coordinate. No matter what you multiply it by, you will never get 1. So there's no way to scale the first vector so as to get the second one. Because of the 0 that the one has at the coordinate that the other does not. Okay, and at this point, we would like to talk about the magnitude of a vector, or the length or the norm. And I'm going to denote the norm of a vector, the length of a vector, by using the absolute value notation. So this will be the length of vector u. And we have two synonyms for the length. So we can always call it the magnitude, or we can call it the norm. And actually, when people call it the norm, the usual notation for norms, which of course could have been chosen instead of the absolute values, is the two lines, but we're going to stick to the one line. So you're not going to see this notation being used in this course. It's a pretty standard notation. By using the Pythagorean theorem once in 2 dimensions and twice in 3 dimensions, we can actually give the magnitude, the length, in terms of the coordinates. So in 2 dimensions, we can see that the vector AB has coordinates, that has coordinates AB, has length square root of a squared plus b squared. This is by using the Pythagorean theorem once. And in 3 dimensions, we can see that the vector ABC has coordinates, has magnitude, square root of a squared plus b squared plus c squared. And this is something that will carry over immediately to any number of dimensions. We're working with 2 or 3 dimensions, but it's a good idea occasionally to note what things carry over. And pretty much you will see that with very few exceptions, everything that we do in 2 and 3 dimensions carries over to as many dimensions as we like, finitely many always. So here, if you had 14 dimensions, for example, if the dimension was 14, you would have 14 coordinates, and you would have needed to take the square root of the sum of the squares of the 14 coordinates, and you would have got the length of the vector. Again, just in case, just in order to make sure that we understand how this works, let's do a little example. So find the magnitude, the length of the vector 1, -3. And when you're done with that, also find the magnitude of 1, -2, -3. Okay, again, pause the recording do it. I'll give you a couple of seconds. And here's the first one. For the first one, it will be square root of 1 squared plus negative 3 squared, which is square root of 10. And for the second one, it would be square root of 1 squared plus negative 2 squared plus negative 3 squared, which is the same thing as square root of 14. Okay. At this point, I should give the formal properties of the length of a vector. So the properties are as follows. The first property is that the length of a vector is always a non-negative number. It is 0 if and only if the vector is the 0 vector. If we scale a vector by a real number, then the length of that will be the absolute value of the real number times the length of the vector. Here is kind of interesting. We have two absolute value notations. The one is for a number, the other is for a vector. Some people might get confused here, but if you remember, if you just pay attention at what the content of the absolute values is, then you will never be confused, because if you have a number inside, you know you're taking the absolute value of a number. If you have a vector inside, you know you're taking the absolute value of the length of the vector. And the last property, which is usually referred to as the triangle inequality, says that the magnitude of u plus v is less than or equal to the magnitude of u plus the magnitude of v. Why do we call it the triangle inequality? If you have two non-parallel vectors, then you have u here, you have v here, you have u plus v here, and this property pretty much tells you that the any side of a triangle is less than the sum of the other sides. Why do we have the equality? The equality happens to be true if the vectors are parallel and point to the same direction. We're going to say that a vector is unit if its length is 1. For example, here's a unit vector, 1 over square root of 2, negative 1 over square root of 2. And if you take the magnitude of this vector, then you can easily see that it's square root of 1 over square root of 2 squared plus negative 1 over square root of 2 squared, which is square root of 1/2 plus 1/2, which is square root of 1, also known as 1. If you think about it, if you take all unit vectors and you make them originate at the origin, their endpoints will describe the unit circle. So you will find all the other unit vectors as originating at the origin and terminating at the unit circle. And if you are in 3 dimensions, you will get the unit sphere, of course. And you get all those vectors terminating at the surface of the unit sphere. There is a very simple mechanism that allows us to find as many unit vectors as we like. It's called normalization. So, and here's how it works. If U is a non-zero vector, then by scaling U by the reciprocal of the magnitude, we get a unit vector. Let's do a quick example. So if we take U to be 1, 3, -5, well, what is the length of U? The length of U will be square root of 35. How did I find 35? 1 square is 1, 3 square is 9, 1 plus 9 is 10, -5 square is 25, 10 plus 25, that's square root of, that's 35. So the magnitude is square root of 35. And this means that the vector 1 over square root of 35, 3 over square root of 35, and -5 over square root of 35 is a unit vector. So this works marvelously in this case. Finally, I would like to add one more interesting fact that we can describe equations of geometric figures based on the things that we saw today. So for example, if you ask what is the equation of a circle centered at a point AB with radius r, then you can think about it the following way. Take a point xy on the circumference of this circle, then the vector that originates at AB and terminates at xy has coordinates x minus a and y minus b, and its magnitude should be r. So if we take the magnitude of this vector, we find x minus a squared plus y minus b squared is equal to r, which gives us the usual equation for the circle centered at AB with radius 1 that hopefully we all know, which is x minus a squared plus y minus b squared is equal to r squared. And this equation has to be understood in the following way. A point belongs to this circle if and only if it satisfies that equation. Conversely, or that's all actually. So if a point belongs to the circle, it satisfies the equation. If it satisfies the equation, then it belongs to the circle. And when I say satisfying the equation, I mean its coordinates satisfy the equation. So it's not now hard to imagine how this would work in 3 coordinates. You would have a sphere, of course, here, centered at ABC with radius r. And analogously, you're going to find the equation again. It's going to be the same thing. So you're going to take your generic point on the surface of the sphere, then the vector x minus a, y minus b, z minus c. That's exactly the vector that originates at the center of the sphere and terminating at the randomly chosen point on the surface of the sphere will have magnitude r. And so the fact that it has magnitude r shows that the equation is given by x minus a squared plus y minus b squared plus z minus c squared is equal to r, giving the equation of the sphere as x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. And that's the equation of a sphere centered at ABC with radius r. And that brings us to the end of our lecture. Thank you for watching.